So now what we have is we have three energy forms: kinetic energy, potential energy, and internal energy. And the sum of those three make up the total energy of a substance. So we have E, so this is the total energy, is equal to U plus KE plus PE. And if I divide by M, by the mass, I'll have each of these in a lowercase or per unit mass basis. So I could have E is equal to U plus KE plus PE. And sometimes we like to use it on an individual mass basis, sometimes on a total mass basis, depends on the application. So now let's consider, at last, the conservation of energy for a closed system. So I have this closed system. So I have a closed system here. And it's going to have E1 initial, E2 final, and it's going to receive heat, and it's going to receive work. So very cleverly what we say is that the difference between the two energies is the amount of energy put in. So we're going to say energy in, energy out minus energy in, or energy initial minus energy, let me write it down and then I'll say energy final minus energy initial is equal to the energy added. And you're going to say, I knew that in kindergarten, so why are you telling me now? So the energy final, E2 minus E1, is equal to energy added, Q, is positive, but work in is negative. And so now if I rearrange this, put the work over on the other side and switch things around, we have Q is equal to delta E plus W. And this is the first law of closed system. And so we're going to look at this in its various forms for a long time. I could write this on a differential basis, so I could say del Q is equal to dE plus del W. So this is the first law for closed system written on a differential basis. Notice that for a property I used D as a derivative, and here I'm using del as an infinitesimal. These are path functions. Heat and work are path functions, so mathematically I have to write them differently to show that path function relatedness. Okay. If now I write work as PdV, I'm talking about an equilibrium or reversible process. So this is true all the time for reversible, irreversible, whatever happens, this is true. For reversible processes, reversible or equilibrium process, I can say that del W is equal to PdV, and I'll have that del Q is equal to dE plus PdV. So this is true for reversible and equilibrium processes. And so that is true all the time. And now let's look at an example of this and how we can apply the first law for a closed system. So let's look at problem 320. You may want to stop the tape at this time and go to the book and look up problem 320 and see what's going on. So I have a piston cylinder. It's a gas, and gas, 30 kilojoules, Q out. V1 is 0.14 cubic meters. V2 is equal to 0.055 cubic meters. P is equal to a constant, is equal to 150 kPa. And I want to find delta U and W. And so that's what the problem says. Here's my system. There's the system. I see that the volume's decreasing at constant pressure, so it's being pushed in. So I'm thinking about that. So I'm thinking about what's happening. You're not asked to draw this. So I did a sketch. System is closed. Process P equals C. Is energy involved? And therefore, if energy is involved, do the first law. Do not tell me you don't know what to do. The next thing you do is do the first law. So you've read the problem, you've done all these things, you've thought about what's happening, and now you write down the first law for a closed system. And you said that it's a closed system. So now you know what to do. So we have that Q is equal to delta U plus W plus delta KE plus delta PE. There's no kinetic energy involved, there's no change of kinetic, there's no change of potential energy involved. So we get rid of those terms. Q is equal to minus 30 kilojoules. Why is it minus? Because in the problem statement it said heat was rejected. You have to make that translation. If you don't put in minus, it means you're not thinking thermodynamically. Then we want to find the work. So the work is equal to the integral of PdV. For constant pressure, it's P times V2 minus V1. And so the work is equal to 150 kilonewtons per square meter times V2, 0.055 minus 0.14 cubic meters, where I have that the work is equal to minus 12.75 kilojoules. So it's work going in, so it's minus, and I can solve for delta U. So I have minus 30 is equal to delta U minus 12.75, or delta U is equal to minus 17.25 kilojoules. And for homework, so you do some of this stuff and not just me doing some of this stuff. 3.5, 3.15, 3.37, 3.43. So now what we want to look at are just a couple of things before we move to the first law for open systems. One of them is, there's a topic in the book called energy as a property, and looking at a cycle. And so it's closed and we're looking at a cycle. And so what I want you to look at with this, so you can look at it in the text, and basically for a cycle we know that energy final is equal to energy initial, and that therefore delta E is equal to 0. And from this, when you go through the development, we'll have that the sum of the heat for a cycle is equal to the sum of the work, or W net is equal to sum Q. And that will prove to be very useful later in the course. So we're going to use this throughout the course. So for a closed system, a cycle, the network all the time, reversible, irreversible, whatever, is equal to the sum of the heats in and out of that system.